this post-quantum testnet as quickly as possible. And hopefully by the end of this week, Thomas can prepare a report detailing all of the next steps to get that testnet. Okay, Thomas.
Thanks, Justin. So, hello, I'm Thomas. I work at the EF as a researcher or project manager. You can call me what you want. Yeah, we'll put a slideshow. It'll be better. So today I'm going to present you briefly like the post-quantum Ethereum and more precisely the post-quantum signature aggregation. I will try to do an overview talk. A lot of technical details have been talked this morning, so I will not go again over this, but more about what we have done so far, what needs to be done, and what needs also to be done right now. So about post-quantum Ethereum, as we can see, as you may have heard, like post-quantum things are not just science fiction, it needs to be done. A lot of tech leaders say that quantum computer can become a reality in 5 to 10 years. We don't really know, but this is a really important situation for Ethereum, and we need to be prepared. So right now, the problem is that we have BLS signature enshrined into the consensus, and to prevent like post-quantum attacks, we need to change this model, and we need to have a new signature scheme. So for this, we thought about different solutions, of course, and like XMSS is one of the most promising one. This has been presented this morning, so I will not go again over the details of this, but this is one of the possible candidates. For now, it seems the best one, but we need to investigate also, of course, other possibilities. You have amazing research posts that have been made about lattice stuff and all of these things, so this needs to be open. But the problem with this signature scheme is that the aggregation of them to submit a proof on Ethereum is a bit more complex than BLS, that was very easy to aggregate. And also the signature size. It's a bit larger than BLS was, with 2.5 kilobytes or 3 kilobytes approximately, against only 96 bytes for BLS. So we need to handle like this larger signature and harder to aggregate signature. For this, as XMSS is an hash-based signature, as it was presented this morning, we need first to benchmark hash in Stark. And so it was our first ideas to do this end of last year by hand. And so what we did is that we benchmark a different hash functions, such as classical ones, Blake 3, Ketchak, and like a snark-friendly one, Poseidon 2, over different proof systems to see a bit what can fit and what would be the best choice, both as a hash function and as a prover system. So as you can see on this chart, like Poseidon 2 clearly stands out. This means that with Plonky 3, as you can see on the left, you can prove in a Stark approximately 1 million on a classic 1 million hashes per second on a classical CPU, while the other hash functions such as Blake 3 or Ketchak are way slower. So this leads up to the fact that probably at the moment Poseidon 2 is our best choice for the hash function, and these initial benchmarks, by studying all the proof system and studying the different hash function, revealed principally 3 major hurdles for on-chain usage. The first one was the prover speed. We need something that is fast to prove to be used on-chain for the Ethereum future. We need also something with a reasonable proof size. We cannot afford like 1 or 2 megabytes proof. We need something around like 128 kilobytes, something around this. And also the bottlenecks that we have right now between fry performance and proof size. So I have listed different elements in the table where I put different comments. So first, Poseidon 2 is the best choice for now as a hash function. Second, fry leads to very fast proof, but they are often too large, of the order of 1 to 2 megabytes. Recently, we talked with Giacomo, with the author of the Weir paper, and like Weir is a reasonably optimistic way to do a PCS. Why? Because the prover speed needs to be improved, but we know that there are a lot of rooms for improvement, and we are discovering that each week. But on the other side, this is to very small proof of the order of 128 kilobytes and very fast verification time. So this could be a very promising alternative, and we pushed a lot of effort on this. And we have also 3 different other topics that are under construction and that I will detail over the next slide. So as I just mentioned, at the Ethereum Foundation, starting from this, all of this context, we started to push a real effort. So WHERE basically is a PCS, so a polynomial commitment scheme that can be directly introduced into our proof system to aggregate together signature. So it is based on 2 main principles. The first one is a recursive folding inspired by Steer and Fry. So at the beginning, you start with a very big polynomial problem, and then you shrink your polynomial step by step, round by round, similar to Steer or Fry. Plus, you integrate during each round a sum check that is inspired by Basefold and other works that are doing sum check for having at the end a very lightweight verification. So now if we try to integrate this WHERE PCS into our signature aggregation, we can have very tiny proof of the order of 100 kilobytes that is perfect for us. We can have also microsecond verification, and this is very important to have this low query complexity, to have ultra-fast verifiers that can run on-chain. And we have also, finally, a post-quantum alternative to what we know today. So right now, with this setup, we can achieve on like a quite performant GPU, like a 4090, 1 million hashes per second over a whole proof system with this tiny proof. And on a CPU consumer laptop, we achieved recently like 100K hashes per second, and our final goal is to have 1 million hashes per second to be really performant and be able to consider that as a possible alternative to aggregate the snark. Related to that, we have like 2 different ongoing efforts and 1 started effort. So the first one is the XMSS hair. So it's a work led by Han from the beginning of the year. So it's a transformation, of the XMSS signature into an hair constraint system. You have a repo and a technical note there when you can find all of the details about this arithmetization thing and all of the work that has been done. And also on the side, we have like a PIOP system that has been developed by Emil and that is tightly coupled with WHERE effort, because we can make the 2 together to have a whole proof system to aggregate the signatures. So this basically encodes the entire system into a single multilinear polynomial instead of univariate polynomial on each column, and it uses the sum check instead of the quotient polynomial. So thanks to this, we can have very small proof, and we are starting to optimize things week after week. And we started very recently the recursion effort. We have a lot of background, a lot of research that we have done since a couple of months about the recursion, meaning that we should be able to aggregate together fresh signatures, but also fresh signature with proof of aggregation of signature. This is basically the recursion that was explained by Emil this morning. For that, we have different possibilities and a lot of research to help. We have the ETH-Proof initiative from the Ethereum Foundation, where we have a lot of feedback, a lot of alpha from the different zkVM vendors, and this is a place where we share some numbers, benchmark, solution, and all of the research effort ongoing about the zkVMs. And we have also a lot of academical research paper about like folding scheme, accumulation scheme, lattices technique that can lead to some recursion. So the solutions that we have identified as possible for the recursion are twofold. We have a medium long-term research perspective that is about folding and accumulation scheme, and a short-term solution that is a minimal zkVM. On the long-term side, the folding accumulation technique seems very promising because this is a single mathematical model. You can code that, but we need much more feedback and much more perspective on adoption plus implementation or tooling. We can think about VARP or NEO on the lattice side, but we have at the moment no existing implementation, so we cannot have enough feedback to say that it will be the proposed solution. But on the short term, we have like the minimal zkVM. What is that? As described by Emil this morning, this is a very minimal ZK VM that can handle this recursion. And on this side, we already have a lot of feedback, and we know that it's tractable because we know that all the ZK VM vendors, almost 30 at the moment, have done like general purpose computation with this ZK VM with a lot of different techniques that we can grab inspiration from. But here, our design philosophy will be completely different because we don't need to be general purpose. But we need to be application specific because we only need to aggregate the signature and not do any arbitrary computation. This is not the purpose of this. We need also, as a result of that, a very minimalistic ISA with probably 1 or 2 like built-in coprocessor and not 10 of them. And we need also a very simple predictable recursion model and a very simple memory model. So to finish the talk, I will just mention, and it will open the session about like the roundtable, what else needs to be done. So we need a Python spec. This will be a reference for future implementation to onboard new contributors, to onboard client teams, for them to have a reference for the implementation. This is very important. And this will be a tricky one because we need to have a spec for different aspects. For example, we have the PCS that need to be spec out, we have the PyIOP, we need to be spec out, and we have also probably the minimal ZKVM, the hash function, the signature model, so we have a lot to spec. And also a testnet. So at the moment, we have only worked separately on the signature aggregation problem, but we have never tested compatibility with all the other bucket of works of the Beam chain. So we need to run the model in reality with the other components, the peer-to-peer layer, to know if this will be a good fit, if everything will be okay. So yeah, that is the end of my talk, and that will probably open the roundtable. Thank you.